Hi, everyone. So welcome back. Class is now 3:10, so class is officially started. So last time we talked about Markov chains and Markov chain Monte Carlo, which was a way of sampling from complicated high-dimensional distributions. We didn't finish doing Markov chain Monte Carlo because we didn't actually give you any ways of constructing a Markov chain with the distribution you're sampling from as a stationary distribution. And we are going to get back to that. But looking at just the lengths of the different chunks of things that we need to cover, I figured that it would be better for us to prove some general theorems about the convergence rates of these Markov chains. Because of course, the point is you want to be able to sample quickly from these Markov chains, or there's no point in turning it into a Markov chain. And in some cases, and so that's what we're going to be doing today. We're going to be talking about convergence of the convergence rates. So let's make it a little bit, let's talk a little bit more about what we mean when we talk about the convergence rate of, say, a random walk on an undirected graph. So we're going to start by proving this for a slightly simpler class of Markov chains. Proving it for Markov chains in general is a little bit more complicated, but but as you'll see, the proof is already complicated enough, even for random walks on undirected graphs. So convergence of random walks on undirected graphs. So we're going to be working with the standard random walk in this case, and let's remind ourselves of all the different salient features. So let's start by just giving a couple graphs. So this is an undirected graph with a bunch of nodes linked together in a line. So does anyone want to go ahead and give a guess as to whether or not the random walk on this graph will converge quickly or slowly? Yeah, slowly, because if you start with a random walker here, it's going to take a very long time to get all the way to the end. And so this has slow convergence. And if you have a something that looks a little bit more like, a little bit more grid-like, let's say. And let's connect all these things together. What about this one? Is this going to converge slowly or quickly? Yeah, more quickly. So this is going to have faster convergence because you can reach any other node more quickly than you can in the linear one, where you really just have to go along the entire chain. So this has faster convergence. And what about a slightly more complicated figure? Let's say I have two stars here, and they're connected by a single edge layer. So I might start in any one of these positions. So these are each of our nodes. So this is going to converge quickly or slowly if you have a Markov chain on this graph. Yeah, so this is going to have slow convergence as well, because intuitively what happens is we have this bottleneck. Slow convergence because of this constriction of this bottleneck. And so the intuition we're sort of going by here is, well, if you have a random walker, in order for it to converge to the stationary distribution, it has to sort of explore some large part of the graph in order to get to the stationary distribution. Like if you can't even reach some of the nodes, clearly the probability distribution can't have diffused out towards its stationary distribution. So that's a sort of intuition. And what's happening here is in this particular graph, even though we have highly connected cliques on either side, it takes a long time for the random walker to go from one side to the other side. And this is the notion that we're going to formalize in today's lecture. And it turns out that this is one way of getting at the convergence time of a Markov chain. It is looking at these sorts of bottlenecks. So let's start by reviewing all the formalism. So we're going to start with an edge-weighted undirected graph. Undirected graph with weight W sub xy. Note that since this is an undirected graph, this is also going to be equal to the weight going from W to YX between vertices X and Y. Okay, and we're going to define a couple of graph theoretic terms. So let's define W sub X to be equal to the sum over all Y, where these are all the other nodes of WXY. You may have heard of this referred to as the degree of the node. Okay, so it's basically the weight of all edges connected to a single node. And once we have that, we can formally define the standard random walk we talked about last time with this probability. WPXY is going to be WXY divided by WX. So this is going to be the Markovian transition probability. Markovian transition probability. And important note, PXY is not equal to PYX because they have slightly different normalizations. So even though our graph is symmetric and the weights are symmetric, the transition probabilities is no longer a symmetric matrix. And if you want to think about this a little bit more linear algebraically, if you had an adjacency matrix, which some of you may be aware of, it's just the matrix A that is composed of all these weight terms. Then what we can do is we can let D be equal to the diagonal matrix with A times the one vector on the diagonal. So of course, this thing here is just going to give you the degree matrix. So then the transition, the Markovian transition matrix is just going to be D inverse times A. Okay, where D inverse is then just going to be W1 inverse through Wn inverse 0, 0. Okay, so this would be how you'd rephrase all these things linear algebraically. We're mostly not going to use that formalism. We're going to just work with indices, but just to connect it to any other graph theory courses you may have taken. Okay, so once we have that, we can figure out the stationary distribution pretty simply. So then the stationary distribution for this Markov chain is simply that each node has probability mass proportional to its degree. So Wx over W total, where W total is just the sum of all the degrees. Okay, and it's pretty easy to show that this is actually the stationary distribution by some of the results we showed last time. So note that pi x times pxy. So the probability of starting at node x and leaving to go to node y is equal to Wx divided by W total times Wxy divided by Wx, which is equal to Wy divided by W total times Wyx divided by Wy, which is of course equal to pi y times Pyx. Okay, so this is actually stationary because the flow from x to y is the same as the flow from y to x at this probability distribution. So now the question is, how fast, if you're starting from some arbitrary probability distribution, do you converge to the stationary one? So you can also think of this in linear algebraic terms as how quickly do you approach if you just repeatedly hit a random vector with your matrix, how quickly do you approach the dominant eigenvector? This is entirely equivalent. So in order to solve this, we need to first, of course, define what it means to approach the stationary distribution. So let's fix some epsilon greater than 0. The epsilon mixing time, So the epsilon mixing time of a Markov chain, this is of any Markov chain, not necessarily one that's coming from the standard random walk in the undirected graph, is just going to be the minimum over probability distributions. So these are all possible starting probability distributions of t, given that the average over at time t of all the different probability vectors minus our stationary distribution, that distance in the one norm is less than epsilon. So we're looking at the first time such that the distance between an arbitrary starting probability distribution and your stationary distribution is less than epsilon. And of course, here we're using the same notation as last time, where our a vector, a of t, is equal to 1 over t times p of 0 plus p of 1 plus dot 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 plus p of t minus 1. Okay, so again, we're not doing just p of t because the weird stuff happens with the with certain types of graphs and parity issues. So instead, we're taking this average probability distribution as time goes on. Any questions about that? So all we're doing is we're basically defining the epsilon mixing time as how long does it take before any probability distribution is not going to be too far off from your stationary distribution. And let me draw this out a little bit. So basically, if we, where am I? If you had some, let's say you had a bunch of points here and you had some probability mass in all of them, you might start with the probability point mass here, and then over time, it's going to diffuse outward. And so at some point, it's going to diffuse out to the same amount on all of them. And so basically, how long does it take before it's not too far off from completely diffused? Okay, so now we've defined the epsilon mixing time. Let's formalize this notion of this bottleneck. Like, what does it mean for there to be a bottleneck? Well, that's basically asking, what we care about is how much flow. So we're basically talking about these flows of probability mass, right? So if you think about it, the epsilon mixing time is just how long does it take for probability mass from point masses on the particular node to sort of diffuse outward until you've reached your stationary distribution. And so we're looking at these probability flows. And one thing you might ask is, well, how much flow goes across a particular connection? Say this bridge here, how much flow goes across this bridge as time goes on? And if you have bridges that aren't carrying very much probability mass, then that will slow down the time it takes until you can converge. And so we're going to define a term called conductance that formalizes these notions. So for a subset, S of our vertices, well, let's first define pi of S as just the probability mass in all of those, all of that subset of the vertices. Okay, so this is the probability mass at the stationary, at stationarity. Then we're going to define the normalized conductance. Well, let me put that in red. Normalized conductance is going to be a quantity. Let's use capital phi. Phi of S is going to be equal to a sort of ugly sum, but we'll see that has a nice intuitive explanation in a moment. The sum over xy in the set S bar. So basically over all edges. So we're looking at all edges between your set S to something not in your set S. Pi x p x y over the minimum of pi of S and pi of S bar. And note here, I'm using S bar to mean B minus S. Okay, so the top is basically saying that for every one of these edges going, and of course, even though we're looking at all pairs from S to S bar, if there is no edge between them, then Pxy is going to be 0, so it doesn't really matter. So you can think of this as from every edge going from S to S bar, how much what's the chance that you're going to be on the starting point of that node, so X in S, and then what's the probability that you're going to jump over onto the other side, so leave the set S and move over into S bar. So let's write down that interpretation. So interpretation. Oh, and note one other thing, which is that this top part here, this is almost symmetric in some sense, right? Because pi x pxy is equal to pi y pyx, since we're at stationarity. And so you can sort of swap the positions of S and S bar, and the top is still going to remain the same. And we've defined it so that the bottom also remains the same because we defined it as the minimum of the probability masses in either of the sides. So without loss of generality, we can just say that we're going to start from the side that has less probability mass. Say pi of S is less than or equal to pi of S bar. So start in the smaller side. Well, smaller in terms of mass at stationarity. Well, if we do that, then the formula becomes simpler. And then the formula is just the sum over pi in S of pi x over pi of S times the sum from y in S bar of pxy. Okay, so I've rewritten it a little bit, but this form has some nice interpretations. So this is the probability of being at X if in stationarity and in S. Okay, just the probability of starting from a particular place. And this here is, of course, the probability of leaving S in one step. Okay, so basically what conductance means is you're going to start from whichever side. So you were talking about this as a set, but you should really think of it as a set and its complement. So whichever side has less probability mass, what's the probability of leaving that side and going over to the side with more probability mass? Okay. And as a note, we can already start interpreting this. So this is going to be a little bit heuristic. This isn't going to be a full formal proof, but we can look at how long it takes to leave S. And of course, if you're going to be able to cover every location in your Markov chain, you need to be able to leave, well, your set S and go over to the other side, right? So how many steps does it take to leave? So the expected number of steps to leave S, well, what's the probability that you're going to leave S in one step? Or have I lost all of you? It's going to be phi, yeah, because we have all different nodes from letter in S. And so phi is sort of combining all that together. So the probability that you leave in one step is just phi of S. So this is one step. What's the probability that you'll leave in two steps? Exactly two steps. So what happens if you leave in exactly two steps? What do you have to do in your first step? Yes, you have to stay. So you can't leave in the first step. So you have the probability that you're going to stay in the first step, and the probability that you leave in the second step, which is just phi of S again. Oh, sorry, these all have of S's. And of course, we're taking an expectation of, we're trying to find the expected number of steps. And so you have to multiply this by 2, since this is a 2-step. So this is leaving in 2 steps. And we can do the same for 3 steps. So 3 steps, 1 minus phi of S. And here we square it because you have to stay the first 2 steps, and then you're leaving in the 3rd step, and so on. So you get some infinite sum. And well, we know how to work with infinite sums. This is stuff that I teach my calculus 2 students. So just recall that 1 over 1 minus x is the sum from I equal 1 to infinity of xi. And therefore 1 over 1 minus x squared is equal to the sum from I equal 1 to infinity of I times x to the I minus 1, right? And that's exactly what we have here. So if we bring out the phi of s's, you're left with 1 plus 2 times 1 minus phi of s plus 3 times 1 minus phi of s squared plus dot dot dot. So that is just equal to phi of s times 1 over 1 minus phi of s. Am I going to get the right number of parentheses? Sorry. Those two match up, that's a 1 there. Squared. But of course, that's just 1 over phi of s. And so in some sense, we have just shown that the expected amount of time it's going to take for you to leave a particular set is precisely 1 over the conductance of that set, assuming you're starting from the smaller set. If you're starting from the bigger set, then it's no longer measuring that anymore because of the way we define conductance. So now, intuitively, we need to be able to leave all the low probability regions in order to mix. So I'm not being very precise here, but the basic idea is if you want good mixing, you don't want to stay in a region with lower probability mass because, well, then you're never going to get epsilon close, right? In fact, you're never going to get closer than half. So you have to leave every S that's not equal to the entire set. So thus, in this way, 1 over phi of S is sort of related to the mixing time. And in fact, you can prove that this is a lower bound on the mixing time. We're not going to do it formally, but that's basically the intuition behind why this is related to the lower bounds on mixing time. One of the reasons this is not a formal proof is that 1 minus phi. Did I make a mistake somewhere? 1 minus phi of s. 1 minus phi of s. I'm not sure. Oh, sorry. Oh, okay. Yeah, great. Sorry, I missed your chat earlier. But yeah, so you were correct as well. Yeah. So now one of the reasons this is not quite a formal proof is because you don't actually have to reach every single region in order for it to be fully mixed, because you can ignore some low probability regions. And so for this reason, it's actually a lot more work to formally prove this, but this is the general intuition behind why this is a good lower bound for mixing time. Okay, so now the next thing we're going to do is this is just the conductance of a specific subset, right? So given a subset and its complement, how long does it take to go between the two? Now, if we want to talk about the Markov chain as a whole, well, maybe you need to look at the conductance of the Markov chain as a whole. And we're going to do that. And so let's define the normalized conductance of the Markov chain. So normalized conductance of the Markov chain. And we're just going to denote it as capital phi without the of s. Chain denoted capital phi is just going to be the minimum over all sets, or all proper subsets. Of lab. Okay. There might be some other edge case, but yeah. So basically, we're saying that the conductance is just going to be the minimum conductance of any like subset in your any pair of subset and its complement in your graph. And let's just write down the note I mentioned a moment ago, which is that omega of 1 over phi. So this overall conductance, this actually is a lower bound on the on mixing time. So it will take this long. We didn't actually prove it, but we gave a heuristic argument for that a little bit ago. Okay, so now that we've done that, that was in some ways the easier part of today's lecture. Now we can move on to the hard part, which is we're going to prove an upper bound on mixing time. So we're going to show that the conductance can also be used to show that you are definitely going to mix within some amount of time. And this is going to be a really complicated and technical proof. So the epsilon mixing time of a random walk, of a random walk on an undirected graph is going to be this ugly thing. It's going to be bounded by O of log of 1 over pi min, which is going to be the minimum amount of probability mass in any of your nodes, divided by phi squared epsilon cubed, where pi min is what you expect it to be. Okay, so this is the big theorem we're going to prove today. Hopefully we're going to finish proving it today. And so let's go ahead and get started. And you'll see how each of the different pieces like comes in as we go on with the proof. So first, we're going to let t be equal to some appropriate constant c times log of 1 over pi min divided by phi squared epsilon cubed for some suitable constant c. So basically, we want to show that for some constant c, this thing is going to get epsilon close to, after t steps, from any starting probability distribution, you're going to be epsilon close to the stationary distribution. And so in order to do this, let's review some notation. So again, we're going to have A is going to be, we're only going to be worried at this particular time t. So we're going to define the vector A to be the average distribution at over the first t steps. P of 0 plus dot dot plus P of t minus 1. And so what we need to show is just A minus pi in the one norm is less than epsilon. Okay, so now we have this A vector, right? Which is what's happened to this probability distribution on average after some time t. And you have this pi distribution. And there are going to be some places where A has more mass than pi and some places where it has less mass than pi, right? Because they both have mass that sums up to 1. And so clearly, in order for there to be a difference, you have to have some places that are bigger and some places that are smaller in terms of probability mass. So let's formalize that. And that'll form the core of our proof, which is we're going to show that probability flows from high mass things to low mass things, relatively speaking. So let VI be defined as AI divided by pi I, And if vi is greater than 1, so if ai is greater than pi I, then node I is heavy, is the terminology the book uses, because more mass is on I at time t than at infinity, on average. So that's not the formal way of saying it, but basically it's heavy if you need to move mass away from that node and move it into some other place in order to get closer and closer to your stationary distribution. And so now once we've done that, without loss of generality, we're going to reorder all of our nodes, re-index so that v1 is greater than or equal to v2, is greater than or equal to v3, and so on. And note that I'm going to say that's also greater than or equal to some vi naught, which is greater than 1. And it's greater than or equal, and 1 is greater than or equal to vi naught plus 1. So basically I'm saying this is the last heavy state. Last heavy state. And of course, this keeps on going until you have all of your nodes. Okay, so we've divided up our set of states into the heavy set and the light set. And so it turns out that if you, this allows us to rewrite this the difference. So then we know that a minus pi in the one norm is equal to twice I equal from 0 to I naught of ai minus pi I, which is also equal to 2 times the sum from I greater than or equal to I naught plus 1 of pi I minus ai. Why are these things true? Yeah, so I mean, it has to do with the fact that you have this balance, right? So here in this piece, we're looking at all of the heavy states. In this piece, we're looking at all of the light states. And so if you look at this difference, basically what you're saying is that all the extra mass in the heavy states, has to be exactly balanced by a lack of mass in the light states. And so the total one norm difference for a to pi is going to be, well, the mass of the heavy states plus the mass of the light states, but the mass of the heavy states is equal to negative the mass of the lights, the missing mass in the light states. And so it's equal to 2 times the extra mass in the heavy states, or equal to 2 times the missing mass in the light states. Does that make sense? Sorry, which epsilon? Oh, so this is equal to some value. And we're trying to eventually show that this is less than epsilon, but epsilon doesn't play a role yet because, well, that's what we're trying to show. Yeah. So all we're saying is that the amount of, if you think about it like you're digging a bunch of dirt, you have some holes that you need to fill and you have some piles of dirt. If you know that at the end of the day, you have a flat ground because you have filled up all the holes with these piles, then that means the amount of dirt in the piles is the same as the size of the holes. And that's all we're saying here. Yep. Oh, probably. Yes, it should, because we don't have a 0th index. Yep. Why is it true that they're equal? Because so we know that the total mass of A and the total mass in pi are both 1, right? Because they're both probability vectors. And what we also know is that there's some spots where, so if you think about it, if you take this difference, right? There are some spots where you have holes in A and some places where you have piles of dirt. Okay, so if you think about this as like piles of dirt moving into holes, the amount of dirt that's above 0 has to exactly match, or otherwise you wouldn't end up with the right amount of dirt at the end of the day. And so these things have to move in. And so the total sum of the extra dirt piled on top is the same as the volume of the holes. Okay, so now that we've done that, we can also rewrite this in terms of our VIs. So this is equal to 2 times the sum from I equal 1 to I naught of VI minus 1 times pi I, which is also equal to 2 times the sum for all I greater than or equal to I naught plus 1 of 1 minus vi times pi I. Okay, so let's just rewriting with our heavy and light notation. So now what we're going to do is we're going to define a new term gamma, which is going to be equal to pi 1 all the way through pi I. Okay, so it's just the total mass from all nodes from 1 to I at stationarity. And we're going to further define a function f, which is going to be from 0 to gamma. Oh, sorry, I think that's gamma I've written down. Yeah, gamma I naught to the real numbers by f of x is equal to vi minus 1 for x in gamma I minus 1 gamma I. What are we doing? All we're doing is we're writing this thing out as a functions so that, remember, you have your big pieces. So you have your, this function f here. We have a bunch of different points along here. So this is just going to be gamma 1, and say this is gamma 2, and say this is gamma 3, gamma 4, and so on, okay? Gamma 5. And what we're doing is we're just saying our function f here is just going to start off at some value, and then when it reaches our next gamma, it's going to drop down and keep on going. Okay. Sorry, hopefully I drew that reasonably clearly. So this is some function, let's call this f of x, which we've defined in this way. And you note that if we define this function this way, basically all you're doing is saying, you can then say that the sum from I equal 1 to I naught of vi minus 1 pi I is just going to be exactly equal to the integral from 0 to gamma I naught of f of x dx. Okay, so all we're doing is we're turning this sum into an integral. Okay, the next thing we're going to do is we're going to do a sort of weird step. We're going to divide up the set 1 to I naught, so all of our states, into contiguous subsets, G1, G2 through GR, to be specified later. So what are these sets? So you might have like G1 is equal to 1, you might have G2 is equal to 2, 3, 4, G3 is equal to 5, 6, etc. all the way. So we're going to specify how we're going to divide them later, but for now, let's just assume we've divided them in this way. Then, given this division, we can define another function, g, from 0 to gamma I naught, also to r, by g of x is equal to us minus 1 for x in this interval gamma I. Okay, so what are we doing here? We're basically just saying that, I haven't defined us yet. So let's let this be us is equal to the max over I in gs of vi. So the largest one, which will always be the first one, the max value in each group. All we're doing now is basically we're going to start at the same place, and we're just lumping some of these groups together. So when you lump these groups together, you get something that's strictly bigger than your original function, g of x, right? And since it's strictly bigger, since g of x is strictly bigger than the original function, that means that this integral from 0 to gamma I naught of f of x dx is less than or equal to the integral from 0 to gamma I naught of g of x dx. And we also know that we can rewrite the integral from 0 to gamma I naught of g of x dx. This is going to be equal to the sum from t equal 1 to r of pi of, so I'm going to abuse notation slightly, but just probability mass contained in all these things from G1 to GT. I guess this isn't actually abusing notation since this is still all set theoretically correct. UT minus UT plus 1, where we're defining ut plus 1 to be equal to 1. And yeah, what are we doing there? We're basically just taking each of these triangles. So we have this triangle here, and then we have this triangle here. Oh, I think I did that wrong. This triangle there. And so on. So we're just taking the total integral of our g function by dividing up this graph into these big triangles, and that's exactly what we're doing here. So this is the base of the triangle. Sorry, not triangle, square. I need to use the right terms. So square, because this is the rectangle. Rectangle is the correct proper term, not triangle, not square. So because we have a base and we have a height. But that gives us the total mass in the integral. And note that if we happen to have 2 times the sum from I greater than or equal to I naught plus 1 of 1 minus vi pi I is less than or equal to epsilon, then we're already done. So we're not going to care about. So basically what we're trying to do is we're trying to show that this thing goes down to epsilon, right? And what we're doing now is we're just bounding it by this other thing that's bigger. The integral under g of x is bigger than the integral under f of x. And so if we can bound that integral, then we've also bound the thing we care about. So if that were the case, we'd already be done. And then what we're going to do instead is we're going to consider the other case. So consider the case where the sum from I greater than or equal to I naught plus 1 of 1 minus vi times pi I is greater than epsilon over 2. So basically, we're just going to consider the other case. In this other case, we know that that implies that the sum from I greater than or equal to I naught plus 1 of pi I is greater than epsilon over 2, right? Because 1 minus vi is strictly less than 1. When, for any subset A of heavy nodes, we also know that the minimum of pi of A and pi of A bar is greater than or equal to epsilon over 2 times pi of A. Why is this true? This is true for a couple of reasons. So this is true because we know that pi of A bar includes all the light nodes. And so pi of A bar includes all the light nodes. So therefore, it's greater than epsilon 2 because this includes all light nodes. Okay, and that's what we just showed. So in this case, this is greater than or equal to epsilon over 2, which of course is greater than or equal to epsilon over 2 times pi of A, because pi of A is less than or equal to 1. And we also need to have the other part, which is, and epsilon over 2 is less than 1 for basically anything we care about. So that means that pi of A is greater than or equal to epsilon over 2 times pi of A. So the reason that we're doing this is, of course, because the minimum of pi of A and pi of A bar is one of the terms in our conductance, right? So in our conductance term, we have this pi of S and pi of S bar term. And so we'd like to be able to bound that when we're working with conductance later. So that's why we've done all this seemingly weird setup. Okay, so now that we've done that, so this is the setup. What we're trying to do is we're trying to bound the mass underneath this function g of x. But of course, in order to do that, we need to define what our sets g1 through gr are. And that's what we're going to do now. So now we're ready because we know what we're trying to do. We're trying to bound that mass. So let's now define g1 through gr. So let g1 just be the set with one element, just one. And we're going to define it recursively. So we're going to start with just a single item. If the first s minus 1 have already been defined, then we're going to define the next one. We're going to define the next one here as let g of s, well, let's give it a starting point and an ending point. Start from, well, k, which is the end of g sub s minus 1 plus 1. Okay, so just the next node. So that's unsurprising. And we're going to let g of s end on an element L defined as the largest integer I, which is of course going to be greater than k, and I is less than or equal to I naught, such that the sum over j is equal to k plus 1 to L of pi of j. So the mass that's in this new segment, this new g, has to be less than or equal to epsilon times phi times gamma k over 4. Okay, so it'll become clear why we chose this particular bound. But basically what we're doing is, if you go back to this original thing, it would be hard to bound the total mass under F, because you basically have every single one of your nodes. And so if you try to do some sort of max bound on the maximum amount of mass in one of your nodes, then all of a sudden you would have way too much mass. And so that bound wouldn't be tight enough. So what we've done is we've divided up all of our original states in our Markov chain, and we've combined them together. So we've lumped them together, and we're going to say we've defined these lumps so that not too much mass is in any of them. And then what we're going to show is that we don't have too many of these. We don't have too many of these groups. We're going to bound the size of R, and once we do that, then we can bound the total mass underneath G. Okay, so that's the general proof scheme. Does that make sense? This is a very technical proof, so please stop me if you followed every one of the steps, but you have no idea what I'm trying to do. Okay, so now we've done this, each of our groups. So where was I? When, by definition, we also know that gamma L plus 1 is equal to gamma k plus the sum of j equal k plus 1 to L plus 1 of pi j. Will I do that right? I think I might have an off by 1 somewhere, but so if I do, please find me. Oh, sorry, we have a question in the chat. Will the sum start at j equal to k, since k is the start of the GKs? Yeah, that would be the case, wouldn't it? I think that is, however, not the notation I have used. So instead, what I'm going to do is I'm going to say that k is equal to the end of the, let's say k, start from k plus 1, where k is the end of the nodes in GS minus 1. Yeah. It is quite possible that I'll have an off by 1 error at various points in this proof. But yes, I think that was already one of them. Yeah. Okay, so let's see. So j is from k plus 1 to L plus 1. That's greater than gamma k plus epsilon phi over 4 times gamma k. And this is by supposition. And so then this is going to be equal to 1 plus epsilon phi over 4 times gamma k. So basically what we're saying is that as our gammas are getting bigger, each time we have the scaling. So when we go from k to L plus 1, so as we do this jump, we're scaling by 1 plus epsilon phi over 4. So then each group G1 through GR scales up gamma by this factor of 1 plus epsilon phi over 4, where we're sort of viewing gamma as a function with respect to the indices. And of course, we know that gamma 1 is equal to pi 1. So if we're going to scale all the way up to the total probability distribution of 1, well, how many times do we have to scale up pi 1 in order to get all the way up to 1? And the answer to that is R is going to be less than or equal to log of 1 plus epsilon phi over 4 of 1 over pi 1 plus 2, because we have the end bits as well. Okay, so basically, how many groups do we need in order to scale up all the way to the total probability mass? And so then this is going to be less than or equal to natural log of 1 over pi 1 divided by the natural log of 1 plus epsilon phi over 4 plus 2, which is going to be less than or equal to 1 over, let's see, log of 1 over pi 1 over epsilon phi over 4. We're using some properties of the natural logarithm where it's, and hopefully got the directions all right, plus 2, which is equal to 4 over epsilon phi times the natural log of 1 over pi 1 plus 2. Okay, so we're almost there. But first, what I'm going to do is I'm going to state a lemma, which we're not going to prove until later, because proving this lemma is a little bit painful as well. So we're going to state a lemma. Oh, wow, I'm already almost out of time. Okay, so maybe I still won't finish this proof today, but I will at least finish it conditional on this lemma being true. So we have a lemma. So our lemma is just going to be that pi of g1 through gs times us minus us plus 1 is less than or equal to 8 over t phi epsilon for all s less than or equal to r. Okay, and we're going to prove this later, probably not actually today. We're going to prove this next week. But basically, this is saying these sizes of these rectangles, basically, right? So the mass in each of these rectangles is going to be bounded by 8 over t phi epsilon. And once we're able to do that, then what we know is that the sum from s equal 1 to r of pi of g1 through gs times us minus us plus 1. So the sum of all these rectangles is going to be less than or equal to r times 8 over t phi epsilon, because that's the mass we bounded within each of these rectangles. And all you have to do is you just need to write all of this out. It's going to be a little bit ugly, but you're going to substitute in the values for r and for, so r here is going to be, we know, what was that? 4 over epsilon phi times log of 1 over pi 1 plus 2. And we also have know what t is, right? So what did we say that t was? We said that t was the c log of 1 over pi min over phi squared epsilon cubed. So we also know what t is. So t is equal to c log of 1 over pi min over phi squared lambda epsilon cubed, and so on. And so you can now throw this all together. When you do all this, it's a little bit ugly, but you'll find that this is less than or equal to 32 over c times epsilon plus 16 pi epsilon squared over c log of 1 over pi min. I will actually put in the online version of the notes, I'll actually put in all the steps of that derivation, but it's all standard algebra. And this is less than epsilon for some c. And we know this because, of course, phi is less than 1 and log of 1 over pi min is greater than 1. And so that would complete the proof, conditional, of course, on this lemma being true. And so, unfortunately, I do not have time to prove this lemma because that's another entire full page on my notes. And so we're not going to have time to do that. But next time when we come back, we're going to prove this lemma. Next time, prove this technical lemma. And then hopefully we'll see how we can actually make use of this conductance thing that we just proved is related to convergence, and show how that allows us to see how certain types of ways of choosing the Markov chain for MCMC works, or how other types of Markov chains converge. And I think I will go ahead and end there for today. So thank you all very much. Hopefully you guys bore with me as we went through this highly technical proof that unfortunately is going to take us 2 days to get through. So I will see you again on Wednesday. Reminder, your homework is due on Wednesday night. So I will try to be in class a little bit before and after on Wednesday. So if you have questions, you can ask me then, or you can ask me on Piazza or send me emails. Yep, have a good weekend, y'all. Let's see. Okay, yep, have a good weekend to everyone in chat. And I will end my recording here. Stop broadcasting and end the meeting. Have a good weekend.